Welcome. Today is October 16th, 2020. Wow, this is pretty amazing. We're up to 7 people for the in-class. I am feeling so excited. By the way, for those of you who want to learn in person, there's still, I think this room is set up for 12 or something like that. So 5 empty seats possible. Today, we're going to talk about a midterm review. And there's a slideshow midterm review, so we're not going to use a lot of Excel today. Instead, this is more a little chalk and talk. And during the midterm review, at any time, if you have any questions, just stop me. Unmute yourself, stick up your hand, do whatever you want, just try and get my attention. Because otherwise, I just motor on. And the reason I motor on is this class is about 51 minutes long and 44 slides, which means a minute a slide. So I'm just like, okay, I got to get through all 44 slides. So, but it's not so important. We do have another class on Monday. So if we don't get through 44 slides, I need to keep telling myself it's okay to slow down and answer your questions. So I'm going to go to the class website. All right, while this is booting up, all right, hopefully you can, for those of you on Zoom, you can now see the class website. And what we're going to do is we're going to go to resources. And under resources is, I think, lecture 13 or 14. Oh, there it is, midterm review, known name. So we'll open up midterm review. We'll stop sharing that and we'll start sharing the review. Yes, when we get to regressions, we can talk about interpreting z-score, r-value, 95%, all the other necessary coefficients. I completely agree. So let's just talk a little bit about the exam, which is actually almost as important as understanding how to do it. Most of you who I'm talking to face-to-face are going to take the exam Tuesday night. I believe it's, what, 7 o'clock? 7 o'clock to 9 o'clock. And how do you take the exam? You just go to the All Sections website and pick tests and quizzes. It looks just like a problem set. The only difference between the problem sets 1, 2, 3, you've done is that it's timed. Maximum of 2 hours. That's it. Oh, and there's a few more questions. Right now, there's 25 questions on the exam. I think problem sets are usually about a dozen questions, if I remember what I wrote for the problem sets. There are basically 2 parts to the exam. They're randomized, so I have no idea how the parts look. The computer puts different parts in different sections. One part is things like, do you remember taking the SAT? Fill in A, B, C, or D, making one of these choices, multiple guess. So there's a bunch of multiple guess questions and a couple of fill-ins where I calculate this number and fill things in. There's a few short essay questions. I don't think I'm giving anything away where some of the short essays would be state the null hypothesis. I mean, hopefully everyone's expecting something like that. Great. And then there are some Excel calculations. So I tried very hard to encourage you to watch the 11 basic Excel videos. I don't know if you did or not. Right now, there's about 400 people taking this class, and only 111 so far as of this morning took the Excel quiz, which is due when? Before the midterm. So the whole idea is to watch the Excel videos and try things out. I had some student who said, oh, I watched all 11 videos, they were great. And then started asking me questions, and I was like, did you do anything or you just watched the videos? He said, oh, I just watched all the videos. I was like, well, there's this file and you're supposed to repeat the steps. It's like, oh, I didn't get that. So the idea is there's this file called List of Boston Prospects you're supposed to download. Let me show you where it is. Stop sharing. Share screen. So if you go to the All Sections website, resources, there is Learning to Excel with Microsoft Excel. And then there's the welcome video, and you're supposed to watch the basic Excel videos for the midterm. And there's this file needed to follow the videos, List of Boston Prospects. So the goal is to download that file and like follow along and see if you could reproduce what I do. Because I'll be honest, I can do it. They pay me to do this, but my goal is to get you to do it. And watching the videos are great, but actually doing it, you know, following, click, 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 type the formula is much better. Quick example, I can talk about regressions all day, but until you actually try the regressions on your own and then try to interpret the coefficients, doesn't mean much. So 2 parts, one is sort of multiple guess, fill-ins, short essays, very straightforward. And the other part is just like the problem sets. Download this file, execute a few commands. What's the result? Upload some information. So hopefully at the end of the exam, whether you did well or you did poorly, you say, okay, it seemed very similar to what I've been doing all semester. My goal also when writing the exam was to write it straightforward. I am not trying to trick and fool you. There are enough students who don't get regressions by themselves that I don't need to be fancy and foolish and, you know, esoteric or anything like that. So if there's 2 ways to interpret a question, my intention was the straightforward way. Does that make sense? A little later today, probably around 4 or 5 o'clock, I'm going to send out an email to everybody. And the instructions for everybody is pretty straightforward. There's 2 exams, one on Tuesday night, one on Wednesday morning. I'm proctoring the Wednesday morning exam. So for those of you on Zoom, for those of you in Russia, Thailand, Cambodia, Dubai, you know, all these places, I'll see you Wednesday morning, Boston time, 8 a.m. And it's relatively straightforward. Just turn on your Zoom on the class website, 477-127-0719, mute yourself. And if there's any questions while you're taking the exam, send me a private chat. Don't chat to everybody. Okay? For you on Tuesday night, for those of you taking the exam, it's the same thing. The only difference is you go to a different Zoom URL, and you have Professor Osher, who's teaching, I think, section H1. It doesn't really matter what section he's teaching. He's just another QM professor, and he's going to proctor you. You just turn on Zoom, shut off your mic, and if you have any questions, you know, send a chat to Professor Osher. And the email will have his Zoom address, since I'll be honest, off the top of my head, I have no idea what his Zoom address is. I have trouble remembering my own Zoom address. So you're in, stop sharing for a moment. Share screen. You get 1 sheet of paper. Students are like, can you enforce that? No, you know, you're in Thailand, right? I cannot guarantee you're only looking at 1 sheet of paper, but this is sort of the honor code, right? We're trusting you to be honest. So you get 1 sheet of paper, you can write as much as you want on both sides, as small as you want, no magnifying glasses, no micron telescope, microscope, all right? You can read it with the naked eye, it works for us. People are like, well, wait a second, we're using Excel, why not Open Notes? My answer is very simple. Open Notes takes longer for you than if I ask you to write out a single sheet of paper. Why? Because you're like, it's somewhere here in this notes, and you spend 5 minutes flipping through every PowerPoint slide until you actually, oh, there it is, right? Open Notes, you organize yourself. You write down the key formulas. You write down what's important. And you're like, oh yeah, there it is. If I say Open Notes, a lot of people say, you didn't give us enough time. If I say closed notes, people will be like, okay, I have to be organized ahead of time. So Open Notes is actually a great detriment. 2 hours, study questions. We're going to talk about study questions in a minute. Any other procedural things? Serenity, go for it.
I was just wondering, do you think that the exam is going to take 2 hours to finish, or are you just like allowing us that time?
So let me tell you that I believe if this is like the spring, which was also done remotely because of COVID issues, during the spring, the average person finished the exam in 1 hour. And the fastest person finished the exam in 31 minutes.
Wow. Okay. Thank you.
There were a number of people who took all 2 hours. There were also a number of people who had computer issues. The number one thing I can tell you, Serenity, people are like, what should I do? Number one, sleep. Even more important than studying the notes, get some sleep. Walking in at 7 o'clock going, oh my God, I have no idea what my name is, all right, is not gonna help you. Number two, strong internet connection. Number three, I'm being serious. You know, I can't tell you how many, I can tell you actually, 12 last semester. Oh my God, professor, the internet dropped, you know, my computer rebooted, the exam got wiped out, you know, 12 people. You get a decent computer, a decent internet connection, you'll do okay. Decent computer, don't buy a new computer, reboot your old computer around noon on Tuesday, okay? If you have 50 windows open and you haven't cleared your cache in 5 months, clear your cache, close all the windows. I can't tell you how many people are like, I can't do it, my computer ran out of memory. How many windows do you have open? Oh, I don't know, maybe 50, 60. Okay, great. Reboot your computer, reboot your mind. Oh yeah, and study too. What else can I help you with? Did that help, Serenity?
Yeah, it did. Thank you.
Okay. Yes, I'm talking, the people who are listening now will be like, okay, I'll reboot my computer. It's the ones who don't hear me that I have to deal with. Anything else procedural wise before we actually talk about content?
Oh, actually, I do have another question.
Sure, sure.
Like, how soon before the test are you going to send out like the Zoom link? And I'm assuming we have to be on Zoom.
We really want you to be on Zoom. Yes. We believe that will make students more honest. And I believe most of the people I'm talking to right now are honest, but there's always, I was honest, how come they weren't? And I heard they were cheating and they were texting each other back and forth. So we're trying to reduce the, they weren't honest. And then who's they? Well, I can't tell you, sir, you know, they're my friend. So yes, please be on Zoom, but muted. When will you get the Zoom link? As soon as the other professors tell me their Zoom numbers. This morning I got, yeah, this is a great message to send to the students. And I was like, and your Zoom number is? So even professors don't read the whole email.
I'm so sorry. I have one more question.
Okay.
Will you have any like extended office hours on Monday?
Monday. Let me tell you, send me an email and I will go home and check my schedule. I have no idea what my calendar is. I'll be honest, I'm a little calendar challenged today. As I walked out the door, my wife reminded me I have a 2 o'clock meeting as well as a 3 to 5:30 meeting tonight. I was like, what? I have a 2 o'clock? Ah, that was my lunchtime. So I'm sorry. If I do have time, I'm happy to hold extended office hours. If I don't have time, I won't. How's that? But I just don't want to promise you now and find out I've already double booked myself. There is 2 optional TA-led review sessions, one on Saturday night, I believe at 10 o'clock, and one on Sunday night at like 7 o'clock in Boston. I sent out about 5 days ago a QM222 email, and it was like the 3rd bullet point. A bunch of people in class are nodding, yes, yes, yes. Was that true? You get that, somebody? Wow, Jason, cool background.
Oh, thank you.
Okay, so there are 2 study sessions and there are a number of TA sessions on both Friday and Monday and Tuesday that are available for extra help in case I don't have any free time. So Feel free to interrupt with any more administrative questions at any time if it suddenly dawns on you I didn't answer one. But let's start going through things. Hopefully now you can see descriptive statistics. If you can't, let me know. So descriptive statistics was one of the first things we talked about in this course. Descriptive statistics were things like the mean and the median. Can you calculate and interpret the mean and the median, which were two different averages? And understanding how the means and the medians move when we add observations to the data set. Real quick, a simple idea of means and medians moving when observations are added is we talked about adding a very rich person like Bill Gates or Warren Buffett or Jeff Bezos. So if we add one outlier, either very high or very low outlier to the data set, the median typically doesn't move at all if it's a relatively large data set, but the mean can move rather dramatically. So adding 1 or 2 points can definitely affect the mean. Adding 1 or 2 points, I mean, assuming you don't have 3 data points. If you have 3 data points, adding 1 point will also affect the median. But if you have a fair number of data points, a few hundred or a few thousand data points, adding 1 more data point typically has no impact on the median. We also talked a little bit about percentiles. The idea of percentiles was to sort of put cutoffs or break down figures and to figure out. So the 20th percentile is the cutoff where 20% of all the data lie below a particular cutoff and 80% lie above. And particularly, we think about these kind of things when we're trying to understand rankings. So instead of thinking about absolute, we'd like to think about percentile cutoffs to know. I'm sorry, what was your name? Kevin.
Yes.
Kevin sits in the way back row of the School of Education.
I was Jeff. Yes.
Yes, you were Jeff last week, right? Exactly. So Kevin looks like a really smart guy, and we'd say, oh, Kevin falls into the top 5 or 10% of all students. All right, so it's a particular breakdown. So knowing Kevin's absolute score, we can turn it into a percentage, and percentages are important because percentages are easy to remember. We also want to know things like poor people. So to be poor, maybe we can adopt a cutoff like bottom 15% of society. What does that mean? If you have an income below this number, you're in the bottom 15%. So we can once again take some absolute number like an income and turn it into a percentage so we can rank people relatively easily. Last but not least, if we're thinking about income, it was a couple of years ago, the top 1%ers, you know. Who are the top 1%ers? Well, what is the income or wealth value to be in the above 99% of all other people in the world? Histograms and bar graphs were the next thing. And hopefully many of you learned about histograms and bar graphs so that you could do the project part A, because project part A, one of the questions asked you to create some histograms. And they're very useful for looking at descriptive statistics because the peak of the histogram, the highest point of a histogram is the mode. Mode is from French, the most fashionable, and it's not the mean or the median. If we have a histogram that is symmetric, what does symmetric mean? Symmetric means we can fold it in the middle, and we draw a line right in the middle of the graph. If we fold the left side to the right side, the two sides match. If you're walking down the street in non-COVID times without a mask on, if people have a symmetric face, you don't pay any attention to them. So think about walking down a major city. You're walking in London, you're walking in Manhattan, you're walking in Hong Kong, Beijing, doesn't matter where you are. And you pass by 5,000 people in about a half-hour walk, just people streaming by you. You don't notice almost anybody until one person jumps out at you. And who jumps out at you typically? Somebody who is non-symmetric. Sometimes it's the clothes they wear. Have you ever seen somebody with like checks on one leg and then like stripes on the other leg? You ever seen these kind of pants or dresses? No? It's sort of like somebody merged two different types of clothes. You're just like, what? Non-symmetric. People pay attention to you. Have you ever seen scary things like pirates or Halloween movies? The slasher is always a big scar or missing an eyeball, right? A non-symmetric face. Non-symmetric things scare the heck out of everybody. You can see 1,000 symmetric faces go, yep, 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 yep. One non-symmetric, you're like, whoa, what just happened here? Symmetry is important. If the graph is skewed left, that means the left side is much longer, okay, than the right side. Right side is relatively short, left side is sort of this way. Think of the left side as somebody who is sort of leaning left, a limp, You know, left leg is kind of short, cut off. Graph is skewed left, the mean is often, not always, but often, you have to sometimes do the calculation, less than the median. Graph is skewed right. In general, the mean is greater than the median, though it is possible to come up with some cases where, I mean, you can always mathematically play with these things, okay? So I can't say 100% of the time. Does that make sense? Should I go on to the next slide? Okay, here's a question, and then I'll be quiet for about 20 seconds, 30 seconds. A data set is information on job satisfaction, which comes from the survey question. How would you rate your overall satisfaction of the job you currently hold? 1, very dissatisfied. Basically, I hate it. 2, somewhat dissatisfied. Yeah, it stinks, but I can put up with it. 3, somewhat satisfied. It's good, not great, but good. 4, very satisfied. Woo-wee! I can't believe I'm so lucky. I get to be a BU professor, okay? That's me, 4. Above is a graph of job satisfaction values from the survey. What's the median level of job satisfaction? And if we can't tell, say not enough. Okay, we have an answer here in class. Tell us your name so Ritvik can give you class contribution. Kira.
3.
Kira says 3, and I would agree with Kira that the median is 3. How do we know that? If we look at this, this is about 4,600 people. This one right here is, I don't know, 4,100, 200, somewhere in that range. So we add the 2 up, and what do we get? We get 4,600 plus 4,200 is 8,000. Anybody? 700 or so? 8,700. This is about 900. So add another 900. So that's about 9,600. And we've got, I don't know, 300 or 400 here. So we have 10,000. Basically, it adds up to 10,000. Nice even number. What's the median? The median would be the 5,000th person. So we're looking for where 5,000 happens. So this is about, I don't know, 400, 300, somewhere in that range. We'll call it 300. This is 900, so that's 1,200. 1,200 plus 4,600 is 5,700. So somebody in this range is the 5,000th person. Because they're the 5,000th person, the median is 3. Does that make sense? Figure out the total number. Look for the person who's halfway between the total number. Which of these statements are above about job satisfaction? Which of these statements are true about job satisfaction based on the above graph? Looks like the exact same graph. A, mean is greater than the median. B, mean is smaller than the median. C, mean and median are the same. Can't tell which. So we already know the median. How do we calculate the mean? I'm going to try an experiment here. Filippo, you're now right below me, so try to let me know if this works. I am trying to show the blackboard behind me. Can you see the blackboard? Oh, you can't. Filippo, can you see the blackboard?
Yeah, it's a little bit diagonal, but we can see it. Yeah, we can only see like a corner of it, but I think it
All
should
right,
be
so
fine.
Filippo, anytime I start going off screen, like writing on the blackboard and you can't see it, shout it out and go, whoa, back.
All right.
All right, I'm gonna find a piece of chalk. We're doing this old school here. So we know what the median is. How do we figure out the mean? So it's relatively straightforward. We've got what, 300 people who have a value of 1. We've got about 900 the value of 2. We've got what, 4,600. Filippo, can you see?
Yeah. Yes, we can see perfectly.
Value of 3. And the last one, 4, is, I don't know, what is that, 4,200 or so, something like that. So we can basically turn these things into percentages. Why? So we got 300 over 10,000 times 1, 900 over 10,000 times 2, 4,600 over 10,000 times 3. So what's this equal to? So it's about 42%, 42% times 4. And yes, you can use a calculator, and you bring a calculator to the exam. What's that? 1.6? We'll call it that. 1.3? 0.8? 0.3? Yeah, maybe about that. So add them all up. 2.9 plus, so we get about 3.9. Let's try it a little bit better. Anybody have a calculator? 42% times 4.
1.68.
1.68, much better. 46% times 3. 1.38. 1.38, perfect. And 9%. 0.9, this is 0.3, so what do we get? 0.7, so this is like 2.1, 3.14, so it's like 4.1. And what's the answer? By doing it that way, if we share our screen, A, the mean is greater than the median. You can also assume it. But students, in the past, when I've said, well, just look, it's skewed. It's skewed to the left. I mean, it's pretty easy to see. They're like, well, how do you prove it? So I just proved it. Okay. But in general, the first time I gave this review session with that slide, I was like, it's just obvious. Just look at it. Make sense? Central limit theorem. So the idea of the central limit theorem is that if data are normally distributed means they come in a bell-shaped curve, then you happen to know, and you know the mean and the standard deviation, then we know 3 rules of thumb. The first is 68, about 2/3 of all observations lie within 1 standard deviation of the mean. We add and subtract 1 standard deviation, we cover 1/3 of all the cases. All right, let's try that again, Jay. Sorry. We cover 2/3. 68% is about 2/3 of all cases. If we add and subtract 2 standard deviations, we're covering about 95% of all cases. And if we add and subtract 3 standard deviations, we're covering about 99.7%. Almost everything. And what is standard deviation? Not error. We'll come up to error in a couple more slides. Standard deviation means it's all the people. So as a quick example, if I'm trying to figure out height, all right, and the US male, average male is 5'9" with a standard deviation of 3 inches, and that's actually what's true in the United States. I looked this up. So in the United States, it's 5'9" plus 3 inches. How tall are 68% of all the men? Add and subtract 1 standard deviation. How tall are 95% of all the men? Add and subtract 2 standard deviations to the mean. How tall are almost all men? 99.7%. and subtract 3 standard deviations. In business, why the heck would we care? You work for an airline. You want to make sure everyone fits into the seats, right? Well, maybe they don't care anymore. But in the old days, they actually cared that passengers could fit in. So you wanted to know what was like 99% of all your customers so they could fit into a seat. Nowadays, everyone just shoehorned in whether you feel comfortable or not. It's just not important. You're making cars. How big do automobiles have to be to fit most people? Tell you a quick personal story. When I got married, I only had a bicycle. I still have pretty much only a bicycle, but my wife had a car. So I married into a car. But my wife got one of the very first Japanese automobiles. She loved it. It was a tiny Subaru. And it fit about 95% of all Japanese customers because this was made in Japan. I got into the car and I hated the car. And she was like, why don't you like my car? And I said, because every time I hit a bump or a pothole, my head slams off the ceiling. It wasn't big enough for me because Japanese men and women were smaller than American men and women. So while they had accomplished plus or minus 3 standard deviations based on Japanese data, they weren't even close for US data. Thank God we got rid of that car. I'd have headaches like every week. It was just terrible. All right, back to the exam. 68% of all men, 5'9" minus 3 inches, which is 5'6". 5'9" plus 3 inches, which is 6 feet. Okay, so that's the range for 2/3. Can you do 95% of all men? Can you do part B? Jeff or Kevin, whichever you feel like being called today.
5'3" to 6'3".
Okay, so Jeff says it's 5'3". How does he get 5'3"? He multiplies 2 times 3 inches. That's 6 inches. 6 inches minus 5'9" is 5'3". Excellent job. Keep going.
And 6'3".
And he adds 6 inches to 5'9". So he gets 6'3". So 95% of all US men are between 5'3" and 6'3". Anybody want to take the last one, part C? Rashad. Don't worry, you're next, Kenzie.
Oh, Professor, would it be 5 feet? The lower
5
limit would
feet
be
is
5 feet.
perfect. Excellent job. Sorry for my over talking you. And what about the high end?
The higher limit would be 6 feet 6 inches.
Exactly. Exactly. Which is 6'6" is 2 meters tall for those of you thinking metric. Thank you very much. Questions about this one? Standard deviation talks about all observations. Now, sometimes we don't know the true mean. So what happens is we need to keep sampling. Quick example, how many people like Donald Trump and want to vote for Donald Trump for president? We don't know until we actually run the polls. Sorry, until we run the election. But meanwhile, this week, next week, we can run polls. We can sample over and over again. When I wrote this exam, I was looking at the age of the typical car or truck being driven on US roads. And since there were about, I'm rounding here, 250,000 cars and trucks on the road, it takes a long time to calculate the true value because we have to go query basically 51 different registry of motor vehicles to find out which cars are on the road. And by the time you do that, the data are outdated and your answer is wrong. So you can actually take a quick sample and we can come up with the true or a better value. So what the central limit theorem tells us is if we keep sampling over and over and over again, then we end up with a distribution where the averages, some averages tend to be on the high side, some averages tend to be on the low side, but most of the averages clump right around the true number. Let me say that again, central limit theorem. If we're trying to take averages over and over again, what we end up with is something that looks like a bell-shaped curve. Because if I grab randomly 100 cars and try and figure out their age, sometimes that group of 100 will have a high average. Sometimes that group of 100 will have a low average. Most of them will be around the true average. So we'll get a bell-shaped curve. The standard error of the mean says the mean I'm estimating, because I keep looking at groups of 100 cars, is not known with certainty. But I can estimate the range that that true mean falls into. And how do you figure out the standard error? It's the standard deviation divided by the square root of n. Standard deviation is, sorry, the standard error is the standard deviation divided by the square root of n. And it tells us the range a particular value falls into. I'm going to go back to Kevin. It's a little hard here. I'm going to flip the picture so you can see what the heck the guy looks like. Give a wave, Kev.
Hello.
That's Kevin there. But yesterday, Wednesday actually, I called Kevin Jeff because I looked at him and I thought he was Jeff, but I was wrong. How many times have you walked down the street and seen someone you think you know, and you're like, whoa, Steve, and they just sort of look at you like, who the heck are you? I've never seen you before in my life. So anytime you look at anybody, there's some chance for an error. As I walk down Comm Ave, I see lots of students, and I'm always looking at your eyes, because if you look at me and go, I'm like, one of my students. And then what happens in my head is I go through a process of like, what the heck's their name? Now I'm staring at Hannah right now, but I'm not 100% sure that's Hannah. I give it about 95% chance when I looked at her, okay? I'm like, could be not, always a chance I have an error. Sometimes I make a big error, like I call Kevin Jeff, all right? And Kevin's like, well, sometimes I go by Jeff, but only by you calling me that, okay? Whole idea of this is very simple. The standard error of the mean is you come up with an estimate for what you think the right answer is, but there's some chance you're wrong. What's the chance you're wrong? Here it's numerical instead of, Kevin versus Jeff. I don't know if that, does that make any sense? Or you just always know who you're talking to and you remember every name of your friends and things like that. Okay. So we sample 100 men in QM222. We find the average male is 5'11". We find a standard deviation of 2.5 inches. So that means compared to the overall population, men in QM222 tend to have less of a range, okay? In the overall population, 95% of all men are between 5'3" and 6 feet. Was that the number, 6 feet? I think so.
Yeah.
And here, everybody happens to be taller on average, but the range is smaller. And why would that be? Why would men in general in QM222 be taller than the average person in average male in US society? By the way, this is true. If we sampled men in QM222, we would find larger heights than the average in US society. There's actually a couple of reasons. Anybody?
Because of our age.
A lot of it has to do with age. So older people start shrinking. There's no older people who are shrinking in the data set. Also, who ends up at BU? A lot of poor people or a lot of well-to-do people? Anybody want to make a guess? Well-to-do people. And well-to-do people make sure their children get, not fat, but decent nutrition. Oh, fed. So they get fed. So basically we have a population A that's young and that has been fed for pretty much their entire life. The overall population, not everyone's been fed their entire life. There's a fair amount of food insecurity, i.e. people don't get fed all the time in the overall US population, and the old US population is much wider. Smaller children, older people. So QM222 will have a higher average. We estimate our mean at 5'11", but we only sampled 100 men. So what do we have to do? We figure out the standard error. Standard error, 2.5 inches, which is the standard deviation, divided by the square root of the sample size, divided by 10. So the standard error is 1/4 inch. What does 1/4 inch say? 5'11" is my best guess, but I'm not sure that's the true number. I need to give you, say, a 95% range. What would the 95% range be? Plus or minus 2 standard errors. So standard error, What does a particular value fall into? What's the uncertainty associated with one item? Standard deviation. What's all the items cover? Does that make sense? So estimate for 511, if we want to be 95% sure, it's 511 minus 2 times 1/4 of an inch to 511 plus 2 times 1/4 of an inch. You know, my best guess was 511, but if somebody reports, I'd say, you know, men in QM222 are somewhere between 510.5 and 511.5. Give a range, show some uncertainty. Online, any questions? Those people on Zoom?
Why did you subtract and add 2?
We're subtracting and add 2 because we want to be 95%. If we want to be 68%, we'd add and subtract 1. If we want to be 99.7%, we add and subtract 3. So the more likely you want to be right, the wider the range. The less likely you want to be right, the smaller the range. By the way, standard error, this whole example right here has a lot to do with political polling. Let me just come up with a random number. Anyone have any idea what percentage of the population say they'll vote for Donald Trump? I don't care what your number is, make it up.
46.
46% says Jeff, Kevin. Okay, 46%, and then they always mumble at the end. The poll has a sampling error of 3%. Well, what does 46% mean? Best guess is it's 46%, but to be 95% sure, we have to add and subtract 2 times 3. 2 times 3, which is 6. So Donald Trump could have as much as 52% of the vote or as little as 40% of the vote. Which is why people are like, oh, the Donald's going to lose. And then suddenly he wins because, wow, it could have been up to 52%. There's a whole lot of uncertainty. How do you get reduced uncertainty in any poll or survey? How do you get reduced? Make N bigger. Sample more items. When you sample more items, you divide by the square root of N. So instead of sampling 100, sample 1,000. So there it is. As you increase the number of samples, 10 samples, 100, 1,000 samples, okay, then the mean stays the same. Central limit theorem. As you increase the number of samples, the mean stays the same, moves around, but the standard error gets smaller. So our average should stay about where it is, but everything else. When you take a few samples, the average has lots of error. It can be far off, but it's still the best average. As your sample size grows, your true average gets closer and closer to the truth, but just all that happens is the error associated with shrinks, not the average itself. Yes, the average might change, but it shouldn't. Other ideas, questions, comments? Hypothesis testing. Hypothesis testing is make a guess and then try and figure out if your guess is right. In basically simple terms. So hypotheses are proposed explanations. Proposed explanations are fancy words for this is my hunch, this is my guess. Your hypothesis can be right, your hypothesis can be wrong. So in crime movies, there's always at the very beginning, someone says, it's the butler who did it. And then of course, it's never the butler who did it, okay, at the end of the movie. But the hypothesis is, it's the butler who did it. No, you've never seen crime movies where they say the butler did it? Okay. So if the hypothesis is correct, you know it, the butler admits what happens. And sometimes the hypothesis is wrong. There's 2 hypotheses. There's the null and the alternative hypothesis. Null hypothesis. No difference between the 2 groups. They have the exact same population mean. Quick example of a null hypothesis. I teach 2 sections. This section, B1, and I teach a section 2 hours from now, D1. Null hypothesis is both groups are identical. So I would expect the same mean score, the same average score from the two sections. That would be the null hypothesis. The alternative hypothesis is there's a difference between the two groups. That one group, B1 or D1, is smarter. Now, I'm sorry if anyone from D1 is listening on the tape, because I'm talking directly to B1, but of course we believe B1 is smarter, right? And you're a better group than D1. Please note that when I give this lecture in 2 hours, I'm going to say, of course we believe D1 is smarter. I'm just telling you what's going to happen, okay? So everybody believes their group is better. That would be the alternative hypothesis. The two groups are actually different. Do a hypothesis test, state the hypothesis. State the hypothesis, the two numbers are the same, or the alternative hypothesis, the two numbers are different, and state it mathematically. Second step, construct a 95% confidence interval for your sample. Take the sample mean and add and subtract two standard errors. Third step, check if the population mean, the master, the original figure, is inside that confidence interval you just created. If it is, then we do not reject the null hypothesis. If it's outside that range, we reject the null hypothesis for your sample. Straightforward? Please raise your hand or unmute yourself or say anything on Zoom if this is not making sense. So I think we might have time to do this one because we only have 2 minutes left, and then we'll have to stop and pick this up on Monday. Are marketing managers in your company paid the same as marketing managers in the whole United States? You look up and you see the whole United States marketing managers earn $120,000 a year, and there's a $20,000 deviation. Why? Because some marketing managers are paid more and some marketing managers are paid less. Does that make sense? So just because the average is 120 doesn't mean that some people aren't paid a lot and some people paid relatively little. You survey 16 marketing managers in your company and you find they're paid $115,000 a year, and they have also a $20,000 standard deviation. All right. The question is, are you underpaying or are you just paying the same? Now, for a non-statistician, this is like, what are you, an idiot? 115 is different than 120. Of course they're different. But as a statistician, what you say is there's uncertainty associated with these numbers. So 115 could actually be the same as 120. Let me say that again. 115 could be the same as 120. Does that make sense? Because we're taking this little sample. If it does, you are a quant person. If that sentence makes sense, that 115 could be the same as 120. It's like 1 + 1 might not equal 2. And you're like, yeah, I agree. But sometimes in certain circumstances, 1 + 1 is not 2. So state the null hypothesis. Mean pay for your company is 120,000. The alternative hypothesis, mean pay for your company is not 120,000. Construct the confidence interval. We sampled 16 people. So it's 20,000 divided by the square root of 16, which is 20,000 divided by 4. 20,000 divided by 4 is $5,000. So the interval is 115 plus or minus 2 times $5,000. So the interval is 105 to 125. Since 120 is within the interval, we might be paying the same as everybody else in the world. Wow, pretty good. It's 11 o'clock. I hope all of you have a safe and healthy weekend, and I look forward to picking this up from slide 19 on Monday.
Thank you.
Thank you.
Thank you.
Professor, I'm just wondering, what room are you in? Because I showed up to the one that you're usually in today.